Okay, so it's probably a good idea for us to just do a calculation so we can get used to taking triple integrals. In this case, it's a fairly straightforward problem. You can see that all of our limits of integration here are all constants. Effectively for us, that would be interpreted as just a rectangular box. Again, let's just remind ourselves how we work through these things. We integrate from the inside out, so we'll integrate here with respect to x first. So let's start working on that. So we'll integrate from 0 to 3, and then we do have another integral from -1 to 2. Just rewriting those. Now let's go ahead and integrate that function with respect to x. So we're going to have x squared over 2 times yz squared, treating those as constants. And we're going to evaluate that from the x limits 0 to 1. And then we'll go ahead and rewrite our dy dz. And let's go ahead and do that evaluation next. So evaluating at 1, I get 1/2 yz squared. And at 0, it will turn out to be 0. So I'll just go ahead and leave that off and write dy dz. Again, working through the next layer of integration here, we'll integrate with respect to y. And that's just y, so we would end up with 1/4 y squared z squared. And again, we're evaluating that from y equals -1 to 2. And I'll rewrite our dz, since we have now one extra integration to do. Again, going through and doing the evaluation here, I get the integral from 0 to 3. At 2, this turns into 2 squared is 4, so 4 times 1/4 is 1. So that's just going to turn into z squared, minus the evaluation at -1, which is -1 into y squared, which is going to be +1. So we end up with 1/4 z squared. And we'll throw on our dz. Now we just have this one last integration to complete. And let me just rewrite this one more time. Integral 0 to 3. I've got 1z squared minus 1/4 z squared, which gives me 3/4 z squared. And let's actually put a 2 up there, huh? dz. And finally, we can evaluate then at 3 and 0. The evaluation at 3, just like any other single integral here, it looks like we're going to have 9 times 3, which is 27/4. And we're going to subtract off the value at 0, which is 0. So this ends up being the value of our integral. So one of the things I like my students to do from time to time is check their work. So I encourage you to use a computer algebra system to do that. You can either use Symbolab or Wolfram Alpha or a different one that you may like. In this case, I typically go to Wolfram Alpha to make some calculations like this. But you can see here I've already entered it in, and it does appear that we've got our integral correct. Again, I felt pretty confident about that, but that's all right. It's good to kind of see how these systems work so that when we do want to use them, we understand that we can. In this case, there's one thing I do like to point out here is when we look at how I've entered this in and how the computer interprets regions of integration, I just simply asked it to perform a triple integral. I put in the integrand, and I also then defined the order of integration that I wanted it to compute it in. So all of that is fairly straightforward. The other thing then that you have to pay attention to is how it interprets the limits of integration. So in this case, you'll notice that I actually entered in the outermost limits of integration first, then the second integral, and then the innermost limits, particularly keeping them in design with the dx limits, the dy, and the dz limits. It's not the only way that you can enter things into Wolfram Alpha, but this is how I've kind of come to do it. And I think it actually works pretty well. So you can see down below, it's going to show us what it thinks is the interpretation that we wanted. And we can verify that by looking then at the integral, checking that it is in fact the order of integration that we wanted, that the dx, dy, and dz are listed as they should be. So there you go.